Lesson 4, Transformations of the Exponential Function. In this lesson, we're going to look at how to apply transformations to the exponential function. In Lesson 3, we learned about a new type of function, the exponential function. This is a new type of parent function, and its most general form is of the form y equals b to the exponent x. Recall, b is the base and x is the exponent. The shape of the function will vary, but generally speaking, there's one of two general cases. Let's summarize below. The first case is an exponential function that has a base larger than 1. This function will always have a y-intercept of 1, a horizontal asymptote at y equals 0, and it will have a general shape that looks like this. The second type is one that has a base between 0 and 1, but not including 0 and 1. This function also has a y-intercept of 1, a horizontal asymptote of y equals 0, but it's the opposite of the first case. It's almost like a horizontal reflection. It'll look something like this. And this is what we explored in Lesson 3. One important thing, the base of any exponential function cannot be negative. That's very important. The two cases are always going to be a positive number larger than 1 or a positive number between 0 and 1. In both cases, the following characteristics are true. First off, it has a domain that belongs to the set of real numbers. It has a range that belongs to the set of real numbers such that y is greater than but not equal to 0. There's a horizontal asymptote at y equals 0, no x-intercepts, and a y-intercept of 1. These are the general characteristics of both types of functions. What we're going to do in this lesson is apply transformations to the exponential function. This will involve translations, stretches, compressions, and reflections. We did this back in Unit 2, and we're going to see the same concepts applied to the exponential function. Let's summarize. The most general exponential function is of the form g of x equals a multiplied by b, which is the base, to the exponent of c multiplied by x minus h, and we're adding k to that. As we saw last unit, a determines the vertical stretch or compression, or vertical reflection. Just to summarize, when the absolute value of a is larger than 1, that will correspond to a vertical stretch by a factor of a. If the absolute value of a is between 0 and 1, in other words, a fraction, that will correspond to a vertical compression by a factor of a. And finally, if a is negative, then that corresponds to a vertical reflection, or a reflection over the x-axis. We see a new letter here. I'm using the letter C to represent horizontal stretches and compressions. The reason for this, B now represents the base, and that was the letter I used in Unit 2 for the horizontal stretches and compressions. So this is a new letter, but it plays the same role. When the absolute value of C is larger than 1, that corresponds to a horizontal compression by the factor 1 over C. If C is a number between 0 and 1 in absolute value, then that would be a horizontal stretch by, again, a factor of 1 over C. And finally, if C is negative, then that corresponds to a horizontal reflection or a reflection in the y-axis. H is the parameter that determines horizontal translations. If h is positive, we go h units to the right. If h is negative, we go h units to the left. And finally, k determines our vertical translations. If it's positive, we go that many units upward. If it's negative, we go that many units downward. And generally speaking, we have to perform our stretches, compressions, and reflections before any translations. Let's put this to practice in example 1. We're going to describe the transformations that were performed on the parent function, f of x equals 2 to the exponent x, in each of the following. We have to perform this factoring step before we get a true idea of what the h value is. This will be shown below. In the exponent, factor out the c value of -3, and that'll give you now x take away 2. Now that we've performed that step of factoring out the c value, we can go ahead and describe our transformations. Let's identify the parameters a, c, h, and k. First off, notice that a is 1. Please don't mix up the a value with the base. The base in this case is 2, and the a value would be the number in front of the base. Since there's nothing there, you can think of it like there's an imaginary 1. The c value is -3, the h value is +2, and the k value is 0. So the parent function f of x equals 2 to the exponent x is horizontally reflected horizontally compressed by a factor of 1/3, and translated 2 units to the right. Let's try part B. Notice that there's nothing to factor in this one, so we can go ahead and write out a, c, h, and k. A is -3. This is the number in front of the base. We have a base of 2, a c value of 2, no h value, but a k value of 1. So here we go. The parent function f of x equals 2 to the exponent x is vertically reflected vertically stretched by a factor of 3, horizontally compressed by a factor of 1/2, and finally translated 1 unit up. Moving on to the mapping rule. Recall from Unit 2, this is useful when graphing transformations of functions. The mapping rule tells us that any point x comma y of the parent function is mapped to the point x over c plus h comma a times y plus k. This rule tells you how to arrive at the new x and y coordinates and allows you to quickly plot the points of the transformation. Let's explore this in an example. We're going to go ahead and plot the parent function along with its transformation and then state the domain and range. Let's get started. So we're given the function g of x equals 3 to the exponent of x minus 1 take away 4. First off, recognize that the parent function is f of x equals 3 to the exponent x. Then, looking at the transformation, we see that we have an a value of 1, a c value of 1, an h value of 1, and a k value of negative 4. Let's first create the points of the parent function. So I'll just evaluate the y values. 3 to the exponent 0 is 1, 3 to the exponent 1 is 3, etc., etc. And now we can apply our mapping rule. So recall, we take all of the original x values, and to get the new ones, we divide them by the c value and then add the h value. So we have to take all of our old x coordinates, divide by 1, which is easy enough. Anything divided by 1 is itself, and then add 1. So basically we're just adding 1 to all of the old x coordinates. This is shown here. Then, to get the new y values, we follow the mapping rule a times y plus k. So to get our new y values, we multiply the old y values by 1 and subtract 4. Because anything multiplied by 1 is itself, we just subtract 4 from all of the old y values. This is shown next. And now we can plot the points. So first I'll plot the parent function. Always sketch the asymptote. Only plot the points you have room for, and then draw a curve of best fit. Even though there's only 3 points, we know what the function should look like. It has to have one of the 2 general shapes that we talked about on the first page of the lesson. I'll plot the transformation in a different color. And once again, only plot the points that you have room for. To help us out here, we should sketch the asymptote. Recognize that we had a k value of negative 4. This means everything is moved 4 units down. That includes the horizontal asymptote as well. Now that you have the asymptote in place and 3 points, go ahead and sketch the shape. And that's sufficient for a problem like this. The horizontal asymptote really helps you figure out the direction the function is heading in, and you just need a few points to get the overall shape. All right, let's answer the question. So the domain, any exponential function will have the set of real numbers. Looking at the graph, the range of the transformation is the set of all y values that are greater than negative 4. And finally, the horizontal asymptote is just the line y equals negative 4. Recall, anytime you write y equals a number, that's a horizontal line that passes through that y value. And while we're at it, let me just make a note over here. For these types of problems, generally speaking, the horizontal asymptote is equivalent to the k value. And that will be true for all of these general transformations. Let's try another one. Here we have the function g of x equals 2 to the exponent of negative 2x plus 2. What we should always do first is factor out the c value. Now that we've done that, we can correctly identify that we have an a value of 1, a c value of negative 2, an h value of 1, and a k value of 0. Our parent function is f of x equals 2 to the exponent x. All right, let's get started by plotting the points of the parent function. I'll just fill out the y values in the table below. And we'll get practice using our mapping rule again. Take your old x values, divide by c, and add h. In this case, we're dividing everything by negative 2 and then adding 1. Try it yourself and then compare what you get with what I'll write next. In a similar way, you get your new y values by taking the old y values, multiplying by a, and adding k. So take your old y values, multiply by 1, which doesn't change anything, and then you add 0, which also doesn't change anything. So the y values remain the exact same. All right, let's plot our parent function first. Once again, only plot the points that you have room for. And don't forget to sketch the asymptote. Next, we'll do the transformation in a different color. The horizontal asymptote will be in the exact same location because you're not moving it up or down. And as best as you can, estimate the locations of the new coordinates. All right, and that's roughly what your transformation should look like. The domain again is the set of real numbers. The range is the set of y values that are greater than 0. And the asymptote is the horizontal line y equals 0. Okay, and that was a couple of examples showing you how to use the mapping rule to perform transformations. Rather than using the mapping rule, you're also allowed to perform partial transformations. The nice thing about the mapping rule is that it allows you to perform the transformation in one step. But you may recall what you've used in grade 10. You used the method of partial transformations. Typically, this corresponded to 3 graphs. The first one was a graph of the original parent function. We've been doing that anyways. Then secondly, a partial transformation that accounts for stretches, compressions, and reflections. And thirdly, a final transformation including all translations. Usually a minimum of 3 graphs are required for this, and you should label them just so you don't mix them up. We'll try this approach in the next example. Okay, let's use what I call the grade 10 way to plot the transformation shown below. Here we have the function g of x equals negative a third multiplied by 3 to the exponent x plus 4. Our parent function is f of x equals 3 to the exponent x. In this case, we have an a value of negative a third, a c value of 1, an h value of 0, and a k value of positive 4. In order to use the method of partial transformations, we first have to come up with the parent function. The y values are going to be 1, 3, 9, 27, and 81. We should plot those points on the grid below. Okay, that's the first of 3 graphs using the partial transformation method. Secondly, we create a graph with all stretches, compressions, and reflections. Notice that we're doing a vertical compression by a factor of a third and a vertical reflection. So, to get the new coordinates, you're essentially multiplying the y values by negative 1 over 3. The x values should stay the exact same because you're not doing any horizontal stretches, compressions, or reflections. So I'll plot a second graph where the x values stay the same and the y coordinates are multiplied by negative a third. This is shown next. Convince yourself that this is a graph that has been vertically reflected and vertically compressed by a factor of a third. Finally, we have to perform the translations, so we just essentially take all of our coordinates and move them 4 units up. This can be done on the graph. First, move your asymptote 4 units up. And next, as best as you can, move all of your coordinates, at least the nice ones that you were able to plot, 4 units up on the pink function. And there you go, everyone. That was the method of partial transformations. I'll label the final function g of x. You can use different colored pens and pencils to do this, or even a highlighter. It's a little messier because you need one additional graph, but you're welcome to use either approach in the future. All right, the domain of the transformation is again the set of real numbers. This will be true for any exponential function. The range is the set of real numbers that are less than positive 4. And finally, the horizontal asymptote is the line y equals 4. Okay, moving on, we have one more to go. Let's use the method of partial transformations once again. So our parent function now is f of x equals 1 over 2 to the exponent x. We have a base of a half now. Let's begin by plotting the points. So I'm just generating the y-coordinates from the x values provided. On the grid, plot these coordinates and sketch the horizontal asymptote. Okay, so looking at the transformation, we have an a value of -5, a c value of 1, h value of -4, and finally a k value of 3. In using the method of partial transformations, recognize that we're only applying a vertical stretch by a factor of 5, a vertical reflection, and no horizontal stretches or compressions. So essentially, all of the y values are multiplied by -5 and the x values stay the same. This one is going to be a little more challenging to generate nice points. The reason being you have to multiply all of these y values by -5. As you can see, that's going to generate some decimals. So I'm just going to do it for the first 2 points because it provides fairly nice y values. So the x coordinate stays the same and the new y value would be 1 times -5 or -5. For the next one, a half times -5 is -2.5 or -5/2. And that'll be right about here. And to be honest, everyone, I'll stop there just because the other coordinates are not going to be as nice to work with. But I know what the function has to look like, so I can go ahead and sketch its shape. We did something very similar in Unit 2 with the reciprocal function using the asymptotes and a nice point. Finally, you have to take your coordinates and move them 4 units to the left and 3 units up. Let's begin by moving the asymptote 3 units up. And take the 2 nice points you have, 4 units to the left, 3 units up. And sketch your function. Label the final function as g of x just so it's clear. And finally, we'll answer the domain, range, and asymptote. As always, the domain of any exponential function is the set of real numbers. In this case, the range is the set of y values that are less than 3. And the asymptote is the horizontal line y equals 3. And that'll wrap it up. This lesson was all about transformations of exponential functions. Here's some recommended homework from the textbook. I hope the lesson was clear and enjoyable. Thanks everyone. I'll see you in the next one.